Hello, everyone, and welcome back to part two of writing buffer overflow exploits and how to use them in a real life environment on live 32-bit machines. In the last video, we have covered some basic information about buffer overflows, how they work. In this video, we are going to perform steps to write a valid exploit to take control of a remote machine via a vulnerable application. First of all, I would connect to my remote machine via our desktop. If you do not have this utility installed, you can simply apt install our desktop. Most of the time, it comes with a Windows with the Kali machine itself. Alright, once we are connected to our Windows machine, I would like to point out one or two details about it. First of all, we are going to use Immunity Debugger over here. Make sure to download and install it. And the second application that we are going to run is one server. I will leave the link in description. Now, one server is a multi-threaded Windows-based TCP server that listens for client connections on port 999 by default and allows the user to run a number of different commands that are vulnerable to various types of exploitable buffer overflows. So this application is intentionally vulnerable, so make sure that you're using a virtual box or any kind of VM and you're not testing it out on your real computer, because that's what we don't want. If you're using it on your own computer, then you're exposing it to different kind of threats. So make sure that you're using VM only. All right, go ahead and fire your Immunity Debugger as administrator. Once you are inside Immunity Debugger, click open and attach one server to it. Once the one server is attached, click on this play button to make sure it's in running condition. So back to our Kali machine. Here we are going to use different Python scripts. First of all, we are going to use a technique called fuzzing to find whether it's exploitable or not. But before that, I would like to connect to one server through Netcat to make sure that I have a connectivity. And as we have read, it connects on port 9999 by default. So here we are connected and it says welcome to vulnerable server, enter help for help. Let's type help. As you can see, there are different commands over here, but today we are after this tron or tron command. Let's type it out, tron 1212, and it says tron complete. That means tron needs a delimiter and then some sort of argument. In case if we want to run it without a delimiter, it says unknown command. So keep this information in your mind for a while, that it needs a delimiter, because that will help us in writing a valid exploit for it. Let's get out of it. So I have written few Python scripts for the exploit, and I will share it one by one. So let's go ahead and open it. It's already open over here. So we are going to use a module called buffers, where you can read more about buffers, and they have their whole documentation available on it. So our host is the machine that one server is running on, and it's running on port 9999. As you can see, I have given one variable over here called app title, and this is the title that we get exactly whenever we connect to one server over here. So this script actually uh, make sure that we keep getting the connections after sending bunch of data to it. As long as we are receiving this title back, that means we are connected. So as you can see in the function over here, as long as we are receiving this title, we are connected. And once we are not, it's going to tell us that no title received, and that means we have to come back over here, and we have to see that our application has crashed, and it's going to be in the pause state over here, and we just have to confirm it. So let's go ahead and look at the next function. uh, the next function is a fuzzing module itself. So as I have said, when we write a run command, it needs a delimiter. So we have to specify the delimiter over here, and then we have to keep sending bunch of data to it. So let's go ahead and get into the folder and run our fuzzing script. So exactly what we have done here, as I have explained in the program that we have written, as long as we are receiving this title, we are connected to this vulnerable application. And once we are not receiving the title, that means we have successfully crashed the application. So as you can see over here, no title received. And when we get back to our Windows machine, we can see it's in the pause state, and it says access violation when executing to F2E to F2E. And here is the command that we have sent. It has taken over EAX. The ESP is written over by a bunch of characters. And when we go up a little bit, we will see that it exactly took 10,005 bytes to crash the application. Now take note of this information. These are the last bytes before the application was crashed. So in the next step, we have an exploit which is going to use those exact number of bytes and send a bunch of A's to it. And we have to make sure that we are crashing that application on purpose. And once again, as you can see, there are a bunch of weird characters over here, and I have no idea. Over there, you can read about it in the documentation, but without these weird characters, the run command is not gonna proceed with any kind of operation. So we have to make sure that we are going to add those weird characters over here, and then after that we are going to send a buffer of 10,005 A's. Let's go ahead and fire that script. But before that, make sure to reset this debugger and bring it back to running condition, a running state. So we have ran our exploit, and when you go back to the immunity debugger, you can see that application has been crashed and it has been overwritten. The EIP has been overwritten by the number of A's, and you can see down below here that we have sent a bunch of A's to it, and all the A's are available over here. Exit out of this application, make sure that your debugger is again resetted and the application is in running state. Now we have to find the offset, exactly where this application is taking the information to take over the next memory allocation. To find that exact offset, we are going to use a Ruby script from Metasploit called pattern create. So we'll go ahead and locate pattern create. So here it needs arguments. For the arguments, we're gonna give dash or hyphen L and the bytes that we have found earlier, the number of bytes, 10,005. Hit enter, and it's gonna give you a pattern that you have to send in your next exploit. So just copy it up, go back to your exploit number 2, and paste it here. I will explain it in a minute. So what we are doing here, we are using the same host, the same port, but instead of sending 10,005 A's, we are going to send a random string over here, a random bunch of characters over here to make sure that we are going in a right direction. Again, it's gonna be the same run command with a bunch of weird characters and sending this random buffer there. So make sure that your application is in a running state. Go ahead, save it, and run the exploit number 2. We have to get back into the directory. I forgot that I was in another directory over there. So the exploit number 2 has gone through, and once we go through the script, once we go through the immunity debugger, we will see that we have sent the bunch of random command that we have specified in our script, and the application is definitely in the pause state because it has been crashed by the buffer overflow. So take note of this EIP value over here. We are going to use it, and once again we are going to use another module from MSF, which is called pattern offset. We're going to give the same -L, but here we're going to give it additional query of the EIP that we have taken note of just right now, 386F4337, right here. So it's going to tell us offset is at 2003. Just take note of it. And we are going to use this offset in our next exploit, exploit number 3. Here we are using the same host, same port. Instead of sending A's, or instead of sending the pattern from Metasploit that we have just created before, I have commented out. We are going to send 2003 A's because our offset is at 2003, and then we are going to send 4 B's in the middle, and then rest of them will be A's again. To send the exact number of A's, I will calculate it by subtracting it the total number of buffer size available to the initial size. Let's save that script and give it a go. But before that, make sure that you have exited out that script and you have reset it in Immunity Debugger once again. Click on play to bring it to the running state. Now we have to run our exploit 3, and you can see that once again we have crashed it, and we have replaced it with the bunch of information that we have defined in our functions in our script. So what did we ask the script to do? We asked it to send 2003 A's, then send 4 B's, and rest of them are going to be A's once again. So as you can see over here, we have sent bunch of A's, and then we sent, I have lost it somewhere. There it is. And we have sent 4 B's, and rest of them are A's once again. Now we have to find at what point we have to jump to the ESP. At what point the application jumps to ESP exactly. For that, we are going to use mono module. So what Mona does, it's gonna tell you, just a minute, click on this L to bring the results to the front. So what Mona module tells you that what are the components or DLL files available that are vulnerable enough to give you access into the machine. So as you can see, ASLR false, rebase false, safe SEH false. So that's an ideal component of the application that we can definitely exploit to gain access of the machine. So copy that address over here and get back to your machine, reset it, and click play on it. Just give it a second because it has, I guess, hang or something. All right, anyways, let's go ahead and move towards our exploit number 4 over here. So exploit number 4 tells us that now we have to use 2003 A's and the address that we just have copied. If it is not working, you can go back and generate that script once again. So these are the real time problems sometimes you face. So you have to go with it anyways. So you have to copy the address here, and that address we are going to use in here. All right. So this is the address that we got it from Mona for this vulnerable DLL. Make sure to write in the endian format. You can read more about endian format in the official documentation. So the endian process is that you have to take the last address and you have to put it in the first, and you have to take the first address in this order and put it in the last. That's the endian format. You can read more about it. So once you have written that address right here, we're gonna send a bunch of C's just to distinguish between the values. So it will be a bunch of A's, and then it's gonna be this address, and then it's gonna be a bunch of C's. Rest remains the same. Save it and make sure that your application is in running state, and go ahead and run the exploit number 4. So once you run the exploit, you can see that we have sent bunch of A's, and then we have sent that address with the library that's vulnerable, and then we have overwritten the next memory allocation with bunch of C's, and the application is in the pause state because we have crashed it. So we are going to copy this value over here, and we are going to find the exact point where it jumps the ESP. So here it is. You can see jump ESP over here. Now our next step is to find the bad characters. In case if there are any bad characters that are preventing this application to crash, so we have to exclude them before we write the shell script to take control of this machine via a remote machine. To write the script, we are going to use once again Mona module, and we're gonna say Mona byte array dash cpb, and we are going to specify the null byte over here since it's already a bad character. So this is the byte array. It's gonna give it to you. You can find this byte array directly into the folder right here. So what we are going to do, we are going to take this byte array. It's a sequential number, as you can see, x01, 02, 03, 04, and then it's going to continue until xff. We are going to copy this array into our next script, which is exploit number 5. So what we are doing in this exploit, everything remains same. Host is the same, port is the same. We are sending 2003 A's. We are not sending B's anymore. We are sending this address over here, and we are sending our byte array. And after that, we are sending bunch of C's just to distinguish between the addresses. So let's go ahead and make sure that your application is in running state. Go back to our Kali machine and run exploit number 5. So once you run your exploit, you can see that once again you have crashed the application, and click on this ESP and follow in dump. So when you follow this ESP in dump, that here you can see you have sent out the same byte array over here until I guess till FF. Yeah, till FF, and after FF we have all the C's over here. So now what you have to do, you have to pretty much eyeball it, you know, this pattern that you have sent. You have to find if there is any missing number over here, if there is a bad character over here. So what you have to do, you have to go one by one from 01, 02, 03, 4. So in this case, there is no bad character available. But if there is a bad character, it's gonna seem like 01, 02, 03, and then you're gonna have like probably something else. It's not gonna be 4, and then it's gonna continue to 5, 6, and then when you're gonna be here on 42, 43, and then suddenly it's gonna say 0B or something, and then so on. So instead of like 6C over here, it's gonna say uh, maybe 01 or any other character. So what you have to do, if in case if you find these characters, you have to get back to your script and remove those characters from here. Save the script, run the script again, get back to these results, and make sure that if let's say 6C was a bad character and you have excluded the 6C from here, and when you save the file, when you save this script and you run the script again, you get back to the results. If 6C is gonna be here, That means you have successfully found the bad character, and then you have to move on to the next and next characters until you cannot find it uh, anymore. So in our case, there are no bad characters available, so we are lucky enough. So next step we are going to do is definitely we have to reset our debugger, put it in, put it back to the running state. And now we have to generate the shell code. So to generate this shell code, I'm going to use MSF Venom. Lhost is going to be this machine where I'm going to listen to the connection. I believe it's 107. And L port, we're going to give it 4444. We're going to use it in a Python format. And we're going to give one bad character that we know already. And that's it. So now it has given us the shell code. We're going to copy this up and we are going to our exploit number 6. And here you can see already I have pasted it, but anyways I'm gonna paste it once again over here. So in this script, first of all let me explain what's going on in here. When we generated the shell code, it has encoded it with 32-bit Shikata GANI. So for that we have to give a little bit of space before and after this payload so it can decode properly and run in a proper way. If you're not going to give this spacing, we're going to give it no bytes, NOPs, no operations in the front, and we're going to give these knobs in the back over here. If you're not going to give the knobs, it might crash the application, or it might not, it might work or it might not. So it's better to be on the safe side and give some knobs on the front and knobs on the back of the payload. So as you can see, our initial variables were called buffer, but when we generated the payload, it says buff. So we have to give another variable over here called buffer is equal to buff. Save that script. Make sure that your immunity debugger is resetted and application is in running state. Let's start netcat over here on port 4444 and run our exploit number 5. I believe it is 5. It's 6. Sorry. Exploit number 6. Again, I'm in the wrong directory. And it should have given us the shell. Unfortunately, it has not. So let me see what is going on over here. Yes, I have a specified wrong IP. I was supposed to give the IP of this caddy machine, generate the shell once again, paste it in your exploit, save the file, make sure that your immunity debugger has been resetted and it's in the running state once again. If you don't do it, it's not gonna work. So you make sure that you have to do it every time. So we are listening on port 444. Let's run our exploit, and there we are. We are in the Windows machine. So the mistake was I was supposed to give the IP of this caddy machine, and instead I have given 107. That means that was the Windows machine itself. So let's try making a directory inside. Let's go back to this folder over here, and as you can see that we have successfully created a folder. That means we have full control over the machine. Now we can do whatever we want. We have full control over this machine. So if you have any questions, if you want to know something more in detail, please leave a comment. I will leave all these scripts in the description below. You have to go through every script one by one, try to understand it, and let me know if you have any further questions.